Part D says if the system is then raised to 100 degrees Celsius, will the mixture be homogeneous or heterogeneous? So part A said we added 170 grams, and then we raised the temperature to 100 degrees Celsius. So because the solubility of sodium acetate is 170 grams at 100 degrees Celsius, this solution will be homogeneous because we were able to get all 170 grams dissolved. Part E, if the solution at 100 degrees, is the solution at 100 degrees saturated, unsaturated, or supersaturated? So since all 170 grams is dissolved in 100 degrees Celsius, we don't have more than the solubility and we don't have less than the solubility. So this would be considered saturated. F says, if the system is then carefully cooled back to 0 degrees and no crystals appear, is the system homogeneous or heterogeneous? So what we mean by there is as it slowly is being cooled, it's still dissolved. It's still, everything is clear and everything is aqueous still, so this will be a homogeneous solution. And then G, is the solution saturated, unsaturated, or supersaturated? So remember that only 119 grams can be dissolved at 0 degrees Celsius. But in F's solution, we have 170 grams dissolved at 0 degrees Celsius. So if that is the case, this will definitely be an example of a supersaturated solution. But the second it recrystallizes, because most likely it is going to recrystallize, then it's going to go back to saturation. The solubility of gases are a lot different than the solubilities of solids and liquids. So unlike most solids, the solubility of gases decrease as temperature increases. So it's the exact opposite of what we discussed before, but because we're now dealing with gases. At higher temperatures, gas molecules have greater kinetic energy and are more able to escape into the gas phase. So as we increase the temperature of a gas, those gas molecules are going to start moving around a lot more, causing a lot more kinetic energy. Supersaturated solutions of gases do exist, but are formed differently than supersaturated solutions of solids. A good example of supersaturation of gases is supersaturated carbon dioxide in a carbonated soft drink. So CO2 is dissolved in the soft drink at very, very high pressure. When the container is opened, the pressure is reduced to atmospheric pressure and the CO2 gas becomes less soluble and is released into the atmosphere. So shaking or otherwise disturbing the solution causes more of the supersaturated CO2 to come out of the solution. So a good example of how we were able to get this supersaturated is at very low temperatures and very high pressure, they were able to get a lot of the carbon dioxide gas to dissolve into the soda. So let's say this is now a closed container. The second you open the can and have the ability of the CO2 to escape, the pressure now comes down and the CO2 is now escaping the soda, causing it to become more flat. So CO2 is used to keep that soda fresh, and that's why they will supersaturated with CO2. Let's go into Henry's law. So at any given temperature, the solubility of gas in a liquid is directly proportional to the partial pressure of the gas above the surface of the liquid. We use Henry's law to decide this. So it's written as the concentration is equal to K times P, where K is Henry's law constant, which is dependent on the temperature of each gas and solvent, and P is the partial pressure of the gas above the liquid. Example 13.3 says at atmospheric pressure, the partial pressure of oxygen in air is 0.21 atmospheres. And then it says at this pressure and temperature, Water contains a 2.73 times 10 to the minus 4 molar dissolved oxygen gas. Then it says, what is the Henry's law constant for oxygen in water at 25 degrees Celsius? So the concentration, so Henry's law is the concentration is equal to K times P. And they give us temperature. It's not to confuse us, it's just to remind us that the temperature is constant. So we're not going to actually use that for this equation, but they sometimes will throw that in hoping that it'll confuse you a little bit, but it's just telling us that the temperature is constant. All right. So if C is equal to K times P, and it's asking for the Henry's law constant. So I'm going to divide by P on both sides, and I get the Henry's law constant is equal to the concentration divided by the partial pressure. So the Henry's law constant is 0.0013 molarity per atmospheres. Lastly, when we're trying to mix two liquids, it's important to know the difference between these two definitions. So miscible and immiscible. When we describe miscible liquids, that is when two liquid substances are infinitely soluble. And the reason why is because they have the same type of intermolecular forces. So like dissolves like. If they're both polar, they will be miscible. If they're both nonpolar, they will also be miscible, but you can't have a polar and a nonpolar. An example of miscible liquids are water and ethanol. So water has that hydrogen bonding with the OHs, and then ethanol also has hydrogen bonding. That means that both of these compounds are polar and will dissolve in each other. Immiscible is when you have two liquids that have very different IMFs. So for instance, you'll have something that's polar and something is nonpolar. A great example of this is oil and water. If you have a glass and you mix oil and water, you'll have water on the bottom and you'll have the oil on top. And no matter how much you shake them up, eventually they will always separate. And that is because oil is nonpolar and water is very polar, and they will not dissolve in each other.